What is up, everybody, and welcome to the final lecture of CS 219, day 20. After today, we are going to have a class, but it's going to be the discussion session led by the TA on Thursday, so make sure you attend that. Tomorrow, Wednesday, you will be watching, in lieu of the class, a quantum computing video that I have posted on Canvas. So this is the final day of actual class. We are finishing by covering the last important topic of the book, which is instruction pipelining. And so, without further ado, let's begin. All right, so this is going to be chapter 16 of the book, and the name of the chapter is Processor, Structure, and Function. However, before I do that, I wanted to talk a little bit about what gates are actually made up, what gates are used in the processor, what's it made up of. You know, in the past I have said that there's AND, OR, and NOT gates, but the reality of things is that the one that people love using is the NAND gate. Now let's just make sure that we remember what the NAND gate is. And so the NAND gate is basically the AND gate with a NOT at the end of it. So if we draw the representation of an AND gate, which would be like this, you have two inputs, you can call those A and B, and then you feed it into your AND gate, then we put a little circle there to signify a NOT, then you're going to get your output. And the truth table for this is basically if we have A, B, and output, it turns out that it's just going to be basically, like I said, you know, well, here let's put the four possible inputs. So we got 0, 0, 0, 1, 1, 0, and 1, 1. And, you know, whereas an AND gate would be basically 0, 0, 0, 1, in this case, you flip that around. So it becomes 1, 1, 1, 0. And so you might be asking yourself, why do they choose to use a NAND gate as the main logic gate that are built into integrated circuits and transistor logic, CMOS, and other things? And it turns out because there is something very cool about the NAND gate, which is also served actually by the NOR gate as well. The NOR gate being basically the OR gate but with a NOT as well. And what it turns out is that both of these gates have what is known as functional completeness. And if you remember your CPU 100, we said that we could make just about anything in a computer with three gates: the AND, the OR, and the NOT. And as long as we had three of these, we're good to go. But we needed to have all three of them. If we remove one of these three, then essentially we can't do all of the possible logic that we could think of. We are limited. Well, it turns out that you can go even simpler because, you know, three gates means three completely different things to design and to handle, right? And suppose that you have a program that uses a lot of AND but little OR, and you don't have that flexibility to share back and forth, right? Well, it turns out that a NAND gate or a NOR gate allow you to actually create basically an equivalent of all these three gates using this just one gate. So just using this one gate, we can create an AND gate, we can create an OR we can create a NOT. And by doing so, we basically simplified the idea of having multiple gates to do logic to just having one kind of gate and then just wiring that gate as we need. And so very quickly, let me prove to you how we could actually make those three gates using just an AND gates. The simplest one is just going to be the NOT, right? Because what does a NOT normally do? You know, the NOT, depending on you represent it, basically takes a 0, makes it into a 1, or takes a 1 and makes it into a 0, right? And so how can we achieve that with an AND gate? Well, you know, the NAND gate, like I said, is taking a NOT at the end of it right here. And so it turns out that all you got to do is basically take your input and just wire it to both of those like that. And if you do that, so if you basically wire A and B to come from the same input, so that that's 0 or 1, you achieve a NOT gate. So bam, there you go. you've just created a NOT gate using a single NAND gate. Now, it might look like overkill, but again, the idea is we want to just use one kind of gate for all our logic. It makes life much easier when we're building these things, mass producing. And so, okay, let's move on to the other one. Let's try the AND, okay? So the AND, you could think of how to do this by thinking about what the AND gate does and what the NAND gate does, right? The AND gate is basically, you can think of it as an AND and a NOT in front of it, right? And so, because it's an AND and a NOT in front of it, it's also reversible in the sense that if we take the NAND gate and we were able to feed it to a NOT gate, we could flip this around to being back what a normal AND gate is, right? We could reverse it. All we need is a NOT. And I've already shown you how to do a NOT using just a NAND gate right here. And that's pretty much it. So you go ahead and you put in a regular NAND gate, which is going to give you basically the 1, 1, 1, 0. And then to flip it back to 0, 0, 1, so it's a normal AND, just hook it to what we have up here. Hook it to a NOT that we just created with the NAND gate. So basically take this up here and bring it down and hook it up here. Hook the output to be the input of the next gate. Like that. And bam, you have now created a AND gate using just 2 NAND gates. Okay? And so now all that remains is to do the OR. Right? And so for the OR, that one's a little bit trickier and might take a little bit of critical thinking to figure out. But it turns out that, let's look at this. Let's look at this table. Okay? So we know how to do the NOTs, right? We can hook them up and flip the bits around, right? We know that if we use a NAND gate on one of these inputs, we can flip the inputs, right? And what advantage would we gain by flipping the inputs? Well, let's try to just flip A and B and see what we would get. If we flip A and B around, if we feed it in a 0, 0, for example, we are going to get back a 1, 1. If we feed it in a 0, 1, we're going to get a 1, 0. If we feed it a 1, 0, we're going to get a 0, 1. And then if we feed it a 1, 1, we are going to get a 0, 0. Okay? So if we perform that flip on the initial inputs, which we can very easily do by, again, using that same concept of just hooking up both of the input wires to the same letter here. So do that on each of them independently. We can basically flip around the output. We can basically convert this gate to be just a NOT. Okay? And so now that we've done this, what happens if we feed this input to an AND gate? Well, again, the NAND gate is going to give you 0 only in the situation where you got 1, 1. And then everything else, it's going to give you a 1, 1, 1, right? And so this looks upside down. This right now looks upside down to this, but that's because this is upside down. The counting there, right? But look at that. Based on the original input that we had, which is this, which we then fed through NOT gates, we essentially have created an OR gate, right? Because the only time that we're getting a 0 is when we have 0, 0, 0 here. And that's pretty much what you do. You basically just feed this through another NAND gate. And now we basically created a OR gate. So to summarize, if you want to make a NOT gate using just a NAND gate, you just basically hook both of the input wires to whatever you're NOTing. For the for the AND, all you gotta do is basically do the NAND and then flip the output, because again, the NAND is just it means not AND basically. So basically you're doing, well, I guess in a way you're doing AND not in a way, right? But yeah, that's all there's to it. And then the only tricky one is this one, because you gotta have 3 gates. So yes, you need 3 transistors technically, I suppose you would say, instead of 1 to create an OR. But the big advantage here is that the NAND gate is universal. because you can use every single logic with a combination of these. So like if you were making some cool things on a breadboard, and you're trying to make sure you have enough gates to do what you're trying to do. You go to like a shop. In my head, I'm thinking Radio Shack, but it doesn't even exist anymore. And you go ahead and you buy a couple of AND or and NOT gates, but then you're like, I want to be safe. I want to make sure that I don't run out of a specific gate. Then what would you want to buy? Well, buy a bunch of NAND gates, because you can do anything. So if you run short on OR gates, you can build one out of NANDs. If you run out of NOT gates, in fact, I would say don't even buy a NOT gate. Just buy a bunch of NANDs, because you can achieve the exact same thing with a single gate. It's only with the AND and the OR that you're using more than one gate. But again, at the advantage of you being able to manufacture one. So hopefully you can see why it's much more economically feasible to just build a bunch of these NAND gates and then just basically hook them together depending on the logic that you need. Okay, so just wanted to bring that up a little bit, since we never really touched it, and I think it's a kind of an important concept to know. If you're curious how an actual NAND gate is made, there are different ways of doing it. There's a transistor NAND gate, and there's a logic NAND gate. The transistor NAND gate is using a resistor and a transistor together to be able to connect things properly. I believe the way that you would do that is you have your inputs, which you have hooked up to a resistor. They're different resistors, and then you got your transistor switches, which then you hook these up together like that, and then over here you put another resistor, and then here's your out. Okay, and then again, these are transistor switches. So that's how you'd actually make a transistor NAND gate. But then again, we don't do that. The CPE people do that, right? Or the electrical engineers do that. The logic NAND gate, you would want to ideally do this out of silicon, right? Because you want to be able to stamp them out. And so those wafers are going to be done using this way as well. So anyways, just thought I'd bring that up since we are kind of talking about the processor, right? And there's very, very famous little CMOS little circuits that are made with a bunch of NAND gates that are just together. If you remember those little things, they're like they look like spiders. And then basically they have little NAND gates in here, and they'll have 4 of them, or they'll have, I think just 4 of them, because then they have a ground, and then they have the voltage. So yeah, okay. So anyways, one of them is the 7400 quad, I believe. Okay, so just a bit of an aside, but still useful. After all, we are talking about the processor, so it's kind of relevant to what we're talking about. Okay, so anyways. Moving on back to actually the topic at hand here, let us go ahead and start by refreshing on the idea of what we need a processor to have, okay? And what it does. So the processor does computation using the arithmetic logic unit, and then it controls what is happening with the control unit, which basically controls the movement of the data and the instructions, as required. And then, of course, we need a way of storing memory inside of the processor to speed things up and to have sort of like, what would say is like, what's the word for this? You want to store, if you're doing a computation and you're halfway there, you want to store your work as you're going. So you need to have some sort of memory. If you're doing something like 3 plus 5 plus 6, first you do 3 plus 5, store the temporary information in a buffer or a register, and then add the last part of the computation, right? So you need to have those in-between steps between doing the math. You need to hold that somewhere, right? And so you have some sort of internal memory or registers, okay? And again, hopefully this is all maybe from 218. And so the way that looks like, we've drawn this before, but we'll do a quick picture just in case. We have some sort of silicon wafer, and they get stamped the chips, and so somewhere in here we have registers, and then somewhere the biggest part of this is probably going to be the ALU, which is made up of a couple of things, like there's going to be probably an accumulator even in there, in addition to the registers, or it might just be the registers, might be the accumulators, but there's some sort of status flags as well. There's a shifter, if you're doing bit shifting and so on, maybe a complementer to like the 2's complement, and a bunch of Boolean logic, right? Which is going to probably be made up of NAND gates, like you were just talking about. By the way, a quick review, since I didn't quite talk about it. When you're doing registers and you're shifting, if you see something like a left shift, hope I don't get these backwards, you're going to shift this way, which means that if you obviously you can say the number of shifts you want to do, but if you're just doing a single shift, it takes the last bit here and throws it out, and then inserts a bit over here, and vice versa with the right shift. Again, I hope I don't flip these backwards, but if I did, you just right and left, I might have flipped them. But I think the way that you say the direction here is the way you shift. So a right shift would be shifting to the right, which means that you throw away the last bit here, and then you insert a bit on this side here. Now, what do you insert? You typically will insert a 0 if it's just a regular shift. If it's an arithmetic shift, then it gets a little bit trickier, because if you're doing a left arithmetic shift, you have to look at the sign bit at the end of this. And if it's a 1, then you're going to throw in a bunch of 1s into the remainder. So like let's say this is a 1, and then there's a bunch of 0s here. When you do the shift, it throws away the last bit over here, shifts these bits this way, and the number of shifts you want, and then just fills it with 1s. Although if this was a 0 at the end, then it would fill it with 0s. The idea is to keep the sign bit intact. When you're shifting the other way around with arithmetic shift, things get even weirder, because you still keep the sign bit over here. So really the only stuff that you're shifting out is this. So like you would throw away this part, not messing with the sign bit. So things get a little bit trippy with that. There's also rotation shifts, which, as the name implies, are rotating the bits rather than throwing them away. So if you're doing a rotation shift this way and the number you're looking at is like that, rather than throwing away the 1, you just go ahead and put it over here. And vice versa, if you're doing it on the other direction this way, let's say this is what we're looking at, what you do is you basically take this bit and then just put it over here. Okay? So those are our quick shifting review. I think there's more details of shifting that they talked about it in chapter 15 or 14. I just didn't talk about it in the video, but you can look at, there's a picture there that has a diagram for these things. In fact, maybe I should look at that picture really fast just to make sure I got the left and the right not flipped. Chapter 14, actually, I think. Nope, chapter 13 maybe. I think it's 13 or 14. Here we go. Chapter 13, page 452 and 451. So the right shift is indeed going the way that I thought. Okay, cool. So for example, left shift, as the name implies, goes left, which means that you are throwing away the bit over here, and then you're inserting here the 0. And for the right shift, you're going to the right, and you're inserting the 0 here. And then you got your sign bits. Yeah, they got a pretty good picture there, so you can look at that. Yep, yeah, so I had it right. Oof, okay. I love mixing left and right for some reason. I'm left-handed, so maybe that has something to do with it. So I question myself sometimes, when I'm giving directions and I say turn left and I actually mean turn right. What I do is I remember which hand I write with, and then I flip that to make sure that I don't say the directions wrong. So yes. Anyways, okay. So looking back at this diagram, so that there's some shifting logic in there as well, because shifting can be very useful for certain operations. You saw when we were doing the multiplications how that can be useful, and in general, multiplying and doing exponents with arithmetic shift is actually very nice and much more efficient than trying to do it in a different way. So yeah. In addition to this, I suppose, and one more thing that we'll have in here is some sort of internal system bus or CPU bus. And that's basically the way to connect between the registers and the arithmetic logic unit and also the control unit. And also, there has to be a way out of this to connect with main memory. Hey, puppy. Puppy has arrived. So, okay. And so, really what they talk about in this chapter a little bit is about registers. And so, the registers are that temporary storage or working space. You know, think of it like when you're working on NAND, you got some scrap paper to work on. And the number and functions of them vary between different processor designs. RISC, you got a bunch of registers. CISC, you have CISC is like x86 and RISC is like MIPS, and RISC architectures usually have a lot more registers than CISC architectures do, because there's a limitation about how many registers can you have before they are unnecessary. And it turns out that at least if you ask the CISC people, they say that after X amount of registers, it's unnecessary to use that to have that extra cost and space used in the CPU for registers, because you're not able to store that much information. You can't fetch that much information ahead of time. It just does not come in useful in the way that we write programs most of the time. However, people put that to the challenge when they came out with RISC, which has like tons and tons of registers, and it is pretty fast. So I will leave it as to you to decide what's a better choice. But do know that there are two choices there. Now, there's four kind of main registers out there. There's the user visible registers that are the ones that you can mess around with in assembly, like EAX, EDX, or R1, R2, depending on which architecture you're looking at. And then there's also the control and status registers, which are used by the operating system exclusively, usually. And they can be things like I believe your program counter would be under that case. By the way, for the general purpose registers, which are the user visible ones, there can be different types of them potentially. Like there may be dedicated floating point ones like you're doing in the IAS assignment, but they could also just be like, it's just bits, it's just zeros and ones. You can do whatever you want with it, and you get to interpret how that information is stored, right? So it may contain basically any operand for any opcode and things like that. It could also be used for storing addressings and pointers and things like that. Technically speaking, by making them general purpose, you increase flexibility, but you increase instruction size and complexity. By making them specialized, you go basically you lose flexibility, but you make them smaller, which typically makes them faster because you have less of them as well too. And as for control registers, they usually cannot be set by programs. They can be read implicitly by programs, and there's some condition bits in there as well, and flags that are set by the processor's results, and so on. And they are used for branching, like conditional branch and whatnot. Examples of that could be the program status word and registers for data movement, like the program counter, instruction registers, memory address registers, and those are going to be data movement registers as well. What else? I think that's about it for the registers. Yeah, let me make sure in the book we have user visible registers, control and status registers, which user visible registers is split into 4: general, data, address, and conditions. And control and status, I split into the ones that I said, so which are program counter, instruction register, memory address register, and memory buffer register. And if you want to know more details about each of them, you can read the book. But we have talked about them. Like, for example, memory address register, as the name implies, contains the address of a location in memory. Memory buffer register basically contains a word of data to be written to memory. And of course, these things communicate with your main memory and also with the cache if you have cache in the system. So, yep, that's all about registers. So now we can move on to the interesting stuff, which is going to be the instruction cycle. So we are going to revisit the instruction cycle one more time. And this time we are going to make it even more complicated. So yay! So let me go ahead and pop a picture up here of the instruction cycle. Here we go. So there's actually something here that is new. You might not see it at first, but I'll point it out. So to refresh the instruction cycle, remember that first you have to basically, I guess the program counter starts, moves up 1, and you compute the address where the next instruction is stored, right? Because the program counter is +1. And so next you go ahead and you fetch that instruction, right? And when you fetch the instruction, it's just a bunch of zeros and ones. So now you got to decode the instruction and figure out what that instruction does. So you go ahead and decode it. And then it turns out that it is an instruction to maybe load something from memory. So the next thing you're going to do is that something you need to figure out what it is. Is it an address or is it something in a register already? Because it's possible. It could be something in a register already, in which case it's pretty nice because then you don't have to go to main memory to pull it, right? And of course, I'm saying main memory, but the reality is that you first need to check the caches, right? Hit or miss, cache 1, cache 2, cache 3. If there's a cache 4, which usually there isn't, but there might be. And then actually, if you're doing like supercomputing and there's multiple processors, multiple chips, we did talk about a possible L4, but yeah, and then eventually you go to main memory, or maybe it's not even main memory because you have a page miss, and then you got to go to the hard drive, So yeah, those are all possibilities that are happening in this stage of once you try to fetch it. You calculate it and then you fetch it. You fetch it if it's not in the registers. If it is, then you're good. You don't need to do that fetching. Now, this is the added part here. This indirection. Because what if what you're fetching is actually a pointer, but then you got to dereference that pointer to get to the real location in memory? Remember the whole indirect addressing system we were talking about yesterday? And in general, when you're dealing with pointers in C++, you can think of the idea of like a linked list or something, or just a pointer to a pointer, like if you're making a 2D array or something and put with dynamic allocation. And so that indirection may involve multiple operand fetches. You're going basically back and forth here doing this, computing and fetching. Eventually, you deal with like 20,000 pointers in a row because bad programmers or something, and finally you get the data. And now you got the data in some register, or maybe you put it in the memory. Well, in some register, whatever you loaded, okay? Because it could be like an actual register, like EX, EDX, or whatever. It could also be something like the memory buffer register. Yeah, it could be the memory buffer register, actually, and so on. So then, you do the computation, potentially, right here. Whatever it is. Maybe you were just increasing it +1 because it was like I++ or whatever. And now comes in the next step, which is to store the answer in wherever it has to be stored. Maybe it just needs to be stored in a register and you're Gucci, you're done. Otherwise, you might actually need to store it somewhere in memory. So first, you got to figure out where that is in memory. So you do your operand address calculation. Then you go there, but guess what? Maybe you're putting it back, it was an I++, so you're incrementing something inside your 5-dimensional array or something. Now you got to do all these indirections because you dynamically allocated that 5-dimensional array, going pointer to pointer to pointer to pointer to pointer, finally to get to an actual data value, which means that you're going to be doing this potentially multiple times. And then eventually, finally, you find the real location you got to store it, and then you throw in the stuff in there. And you might have more than one result depending on if the operation involves multiple things, but it might just be one. So this is going to be the extra steps that we're thinking about. Finally, we're done, but hey, not really, because we are going to start out pretty soon with the same thing again. But before we do, we check to see if we got any interrupts. And if we did, then we go ahead and take care of that. That's its own adventure you got to do, right? And eventually, you come back, and then you go ahead and you fetch the next instruction, right? And so, it's a lot of steps. And some of these steps can take longer than other steps as well, okay? And so, with that, I would like to introduce you to a possible way of speeding up this system, okay? Because, let's talk about, for example, about the data flow of reading an instruction, okay? Or fetching an instruction. First, you got the program counter, which contains basically the address of the next instruction. Well, not the real address, because remember, we might have to change that because that's just a counter, but physical versus virtual addresses versus like physical, yeah, all of that, right? But the point is that you have the address there. So you move that to the memory address register, you place the address on the bus, the control unit requests a memory read, The result is placed on the data bus. It's copied to the memory buffer register and then to the instruction register. And meanwhile, this whole time, the program counter is increased by 1, right? So it's a pretty complicated process, actually, even within just each of these individual instructions, right? Furthermore, once you combine a bunch of these, you might be trying to request multiple reads, but the system bus might be busy, or there might be somebody else using it, like if you got the cache involved, right? And so you have cache miss, you got to bring things over. So it's a pretty complicated process in general, okay? However, it is a predictable process because you're always kind of going to be following this whole sort of step. Yes, you might skip some steps, like in the case of the operand fetch, if you're already storing in a register. But that's probably because at some point you had to fetch it and put it in that register, right? So you are going to go at least through this process fully once, and then next time around, some things might still be in register, some things may not. But basically, the fetch and indirect cycles, up here as well and up here are all going to be pretty much predictable. And because of that, we can take advantage of that to do basically instruction pipelining. And so what is instruction pipelining? Instruction pipelining, you can think about like an assembly line, okay? An assembly line is better to manufacture articles than the non-assembly line, because what you do is you have different people. Well, nowadays it could be robots, but let's just say back in the day, like Ford Motors or whatever. You have different people doing different pieces in a conveyor belt, right? So maybe we do some pictures for that. So let's say that we have a little conveyor belt and these guys are building a car, right? Because what was it, the T model or whatever? That was the first assembly line car. And so first, we got, and again, this is not probably how they did it, but whatever. We got the little chassis of the car that they built, okay? And so first there's going to be a dude here, or a guy or a girl, who is going to put in 2 wheels. So when the car moves here, he's going to hook up 2 wheels on that side. And then you got somebody over here who's going to do the wheels on that side. So when the car moves here, he puts in the 2 wheels there. Next, the car moves here, and there's a girl with an engine, and she's going to put the engine there. Now, she's very strong. She can lift that engine, I guess. Okay, or maybe she's got some pulleys to help. I don't know. And then you move over here, and maybe there they go ahead and put in the steering wheel. And then finally, so here's person putting the steering wheel. And then finally, over here, there's maybe one guy, or maybe on both sides here, although they could have done that before with the wheels, I guess. And they're spray painting the car. Okay? So, pimp my ride, I guess. I don't know. Okay? And finally, I guess the last step of the thing is to kind of have a person get into the car. So, that's actually a person sitting in the car, and then there's like a little ramp, and he goes ahead and takes out the car and drives away, to sell the car. Okay, and so that is basically what the assembly line does. However, if you just do one car at a time, all of these workers are lazy, because while the car, if the car is right here, nobody is doing anything on these stages here, right? And if the car's over here, nobody's doing anything in the other stages. The advantage of a assembly line is that you can do multiple cars and have that extra efficiency gained. Because, let's say that each of these steps takes 1 second. So right now we got 1, 2, 3, 4, 5, 6 seconds to build a car. Okay? Maybe hours, not seconds, because it seems kind of minutes, maybe. Okay, let's do minutes. It's a little more realistic, I guess. I mean, none of this is. I mean, you can't put an engine in 1 minute, but whatever. Okay, let's just say it takes 6 minutes. And so The thing is here that if we go ahead and when we put a car here, this guy's putting engines. When it moves to the next step here, we go in and feed in another car so that he can put wheels to this car as well. I meant to say engine, I meant wheels. Okay? And then when these cars move over to the next stage here, now this person is putting wheels over here. This one's putting an engine, and this one is still putting the first two wheels. And so for the first 6 minutes, there is no cars being outputted here. Like this guy, there's a guy here waiting to drive cars. He's just chilling, reading the news, right? What would they read the news? Probably about the Great Depression or something. I don't know. So, yeah. Okay. So moving on, we go in one more step here. Now this guy's putting wheels to this car. She's putting the engine, and he's putting the steering wheel. And here we have another car putting wheels there. Eventually, it moves to the next step here. In this step, I guess back quality control. One of those wheels just fell off. There we go. So now he's putting wheels to that. Well, this one's putting wheels here. Well, this one is putting up the engine. Well, this one's putting up the steering wheel. Well, this one is painting the car. These two are painting the car. Okay, and finally, the next step right here, we actually get one car that is ready to be driven off the lot, or off the assembly line, sorry. But meanwhile, these guys are putting wheels, engines, steering wheel, painting. What happened to our quality? Like, this guy never put wheels on that one, but okay, it's okay, it's okay. It was a test run for them. Yeah. Early days of assembly line manufacturing, okay? So, yeah, but here's going to be the advantage gain. So the first 6 minutes, no output of cars. We had one car, which we did initially, but then nothing happened for the 6 minutes after that. But here's going to be the beauty of assembly lines. Right now, this person is going to drive away this car. But in 1 minute, this car is going to move here and be ready to be driven away as well. And then this car is going to go here and then here. So even though the first, while the pipeline was being populated or filled up, while the assembly line was being filled up, there was no output. Now, instead of having a car every 6 minutes, we're going to have a car every 1 minute because now the pipeline is full. And it's going to keep going like that as long as we keep feeding cars here as the assembly conveyor belt keeps moving forward. That's the big advantage of a pipeline, that we can go ahead and split the task at hand into multiple steps and then perform those steps at the same time simultaneously to be able to speed up the overall process and to cut it, to basically cut it so that, if we go back to now computer science instead of car manufacturing, we can go ahead and see that our instruction cycle state diagram, we can think of these circles each as being one of those persons in that factory assembly conveyor belt line. And so one person can be doing this for one instruction while the person after them is doing it for the next instruction. Or I guess the one before technically, because an instruction arrives here and then it goes here. And when somebody's fetching this, they fetch the operand and then they go ahead and they fetch the instruction. And then they go ahead and fetch the operand. But while this person is fetching the operand for instruction 5, this person can be fetching the operand for instruction 6 in the meantime. And then at the same time, for an instruction that was done earlier, they could be storing the output. So rather than, you're running this, and then when it comes time to fetch, you just sit here patiently waiting for all the nasty pointers to get fetched to finally get the data. You could be doing something in that time, right? And so what happens is, if once you finally fetch it, while you're doing this operation, the next instruction is already being fetched in that meantime, you're going to save that time. Now, it's not a perfect system, but it is definitely a system that is much faster than trying to do one thing at a time. Okay? And so therein lies the beauty of instruction pipelining. Again, something that was taken, not something computer scientists created, but something that was taken from an existing idea of a manufacturing plant. Okay? And so let's go ahead and look at a very simple version of a pipeline, which is what is known as a two-stage instruction pipeline. A two-stage instruction pipeline, we just think of it like a fetch and execute, okay? And so what we're saying is that at first, we're gonna fetch something. We're gonna fetch the next instruction. Then we're gonna execute that instruction. While we are executing the instruction, we are already prefetching, that's a term that's useful to know, we're already prefetching the next instruction to run. And so you can think of that like two people are processing files from a file cabinet. Okay, if you got just one person, that person first has to, let's say that they are looking for, they got a list of names of people who paid their bill for their water. Okay, their water bill. Okay, this is like pre-computer days. Okay, so people, they're opening mail and checking the checks. And their job is not to cash the checks, but just to mark off that they received the payment, so they can send it over to like accounts payable or whoever deals with actually cashing the checks. And so one person, gets the mail, opens it up, sees the name of the person who just filed their payment. Let's say this is Timmy. It says Timmy's got this check. So now this guy has to go to a file cabinet, look up Timmy's file, pull it up, and then maybe check off there that Timmy has made a payment for the month of August, okay? And then once that is done, he goes ahead and puts that file away. Then he goes back to his desks, opens up the next letter, and now it's Jane. Jane made her payment for August as well. So now the employee goes to the file cabinet, looks up Jane's file, checks off that Jane made the payment, and then goes back to his desk, okay? Opens up the next letter, and now it's, John, okay? So here's the thing. Let's go ahead and say that the employee, which we haven't given him a name, but we'll say his name is Executor, the Executor. He goes ahead and hires an assistant named Fetch. And that's going to be her job, actually. Interesting. Her job is going to be to fetch into the file cabinet whoever name Executor tells her to fetch. Okay? And so now, while the Executor is opening a letter, Fetcher is just chilling there, checking WhatsApp, I don't know. And then eventually, going back to the example, the first letter was Timmy, right? So you get Timmy gets her, it might be cooler if I be drawing this. So here we got Executor, which we'll call X, and then we got Fetch. Interesting names. And so here we got the table, and here we got the letters. All right, so he pulls out the letter, and it's Timmy. It's like, well, say Timmy, this guy probably knows these guys by memory because every month they pay, right? And so he goes ahead and gives Fetcher the name of Timmy. It's like, give me Timmy's file, please. He's nice. So Fetcher goes into the file cabinet room. It's like, yeah. And then goes in there and fetches Timmy's file for the water department. Okay? And then, now that she has fetched good old Timmy's file, she goes back and gives it over to the Executor, who can then mark it off as done. Gives it back to Fetcher so that she can put it back. However, while he's potentially doing the marking as done, and now that Fetcher's going to go back and put the old file back, in the meantime, the Executor can open up the next letter, which was from Jane, and figure out that it's from Jane, because it takes time to open letters. They don't want to get paper cuts, so they do it very carefully. And so he can go ahead and tell Fetch to now get Jane's file. So, she goes ahead and gets Jane's file. And she goes back and gives to him. And then he can mark it off and then put it there and so on. So you can see that there's an efficiency gain, because while the fetcher is getting the information from main memory, which is our file cabinet. The executor can be writing the previous person's file or be opening the next envelope and things like that. Now, the sort of limitation here is that typically the execution is going to be faster than the fetching. So there is still probably some time where he's waiting and he's probably like, hurry up and fetch faster, you know? Maybe I should have, I could have used an example of a dog instead of a person, but okay, whatever. But yeah, so essentially, you know, there might be still some extra waiting, but it's still going to be faster because whatever time it takes for executor to open up envelopes or check things off potentially in the file is time that, you know, you're gaining by actually going to fetch the stuff. Okay, so there is some speed up going on here. And so that's basically what the two-stage instruction pipeline is. While we are fetching the next instruction, we are executing the one we just fetched before. So you know, we execute this instruction and we're already fetching the next one. And then hopefully when this finishes executing, we already fetched the instruction. And if we did, then bam, we can feed it up. We don't have to wait for the fetch to happen. However, even if it hasn't arrived yet, we probably have sent a request already, which saves us some time. Okay? So then the book goes ahead and talks about latches, which is a fast register that stores intermediate values between stages. And you can go ahead and read about that and how they basically serve to decouple the stages from each other and how to flow the information between the different layers of this. So you can go ahead and read about latches and whatnot. But I'm going to go ahead and move on to talking about more complicated pipelining systems. And so let's go ahead and analyze, again, these different stages, right? So see how we could pipelinerize, if that is not a word, but let's say it is, this system. And so let's look at these stages that we have. We have a fetch instruction stage, which requires a memory read, potentially. You know, it could be register read, but it could also be memory read, more than likely. There's a decode instruction, which requires checking and comparing this with the opcode list or table. There's a calculate operand, which may involve displacement, as it says here, indirect, register access, and other things like that. There's fetch operand, which is basically another fetch operation, which means memory access potentially. Or yet again, if it's already in register, then we don't need to do anything. That would be ideal, but not always the case. Hopefully this is in cache, so it's a little bit faster, even if we do have to fetch. And then finally, we also have the write operand, which is going to be to write the answer to a file, or sorry, to a file, to a memory. It could also be to store it in a register, you know, it's possible, but it more than likely might end up at the end of the day after the computations have to be stored back into memory. And I guess I didn't mention it, but there's also the execution of the instruction, which again, that's just the computation itself, which may actually be a request to go somewhere else, or it could be a jump or a branch, which is actually going to affect our pipeline as well. So this is what a pipeline looks like. And so this might be a little bit confusing to do or to understand. So I'll try to do the same thing and draw it on the iPad. So let me go ahead and try that. Because I think if you see me build it, and I could have drawn it ahead of time, but I think the useful thing for you is going to be if you see me actually build this to see how it actually gets populated. Okay, I tried a square and I got a circle out of that, but okay. So, well, I guess what I could have pre-drawn ahead of time was maybe the grid. Yeah, you know. Okay. We'll just have to imagine that these are straight lines. I mean, technically they are straight lines. They're just not aligned to other parts. Or to other lines, I mean. They're not parallel. Okay. Good enough. Let's go ahead and say our program has a couple of instructions. Okay? The instructions are going to be, we're going to start with a very simple program where there's no if statements, loops, functions, anything. It's just a bunch of sequential instructions that will always be running the same order, which is the ideal scenario for building the car, which is essentially we're building the same car in the same way every single time, right? Of course, this can vary because, like, imagine now somebody wants a car that has red paint or a car that has 5 wheels because there's a backup wheel that's stored in the back, or it's like a truck with like 6 wheels, you know, that kind of thing, right? So we're just going to go with the most simple example, which would be instructions are always in the same order. And so our program is going to have the number of lines we have in here. So let's see how many we have. 1 instruction, instruction 2, instruction 3, instruction 4, instruction 5, instruction 6. Okay? So it's going to have 6 instructions. And up here, we're going to represent the clock cycle or time. For simplification purposes, we are going to say that each instruction takes 1 clock cycle and that all instructions take the exact same time. This, of course, is an incorrect simplification to make because we know that a fetch instruction may take a variable amount of time depending on the level of indirection required. So basically, if you're accessing a pointer or you're accessing the data itself, or maybe it's already in register, so you don't need to even access it anywhere. And of course, executing is usually the fastest thing because the processor is typically the fastest thing, and the slowest thing is memory. And again, if you have a fetch, it might take longer because there's a cache miss or, you know, it's a cache hit. So again, it's an oversimplification, but again, don't worry. We'll talk about those things and how they mess things up, okay? But even with all these things that I'm oversimplifying, trust me when I say that this thing is faster than not having a pipeline, okay? All right? So, believe, have faith. You need to believe, as Morpheus would say. And because we are going to be using this a couple of times, before I actually start writing on it, let me go ahead and make a copy down here. Okay, cool. So, what are the different stages of an instruction that we could have? So let's say that we're not using pipelining, okay? Let's go and do this the old school way. The first thing we have to do, if we look at our instruction cycle, is we need to fetch instructions. So first, I guess we're going to have to do some abbreviations here, okay? So we're going to use FI, DI, CO, FO, EI, and WO. FI means fetch instruction. DI means decode instruction. CO means calculate operands. If you want to see more about what each of these do, go to page 550 on the book. FO means fetch operands. EI means actually to execute the instruction. And WO means write operands. And these are the ones I just talked about as well too. Okay? And so again, fetch instruction will read the next expected instruction into a buffer. Decode instruction will determine the opcode and the operand specifiers. Calculate operands is going to calculate the effective address of each source of operand. This may involve, again, displacement, registers, and direct addressing, all of these other forms of address calculation. Fetch operand is going to fetch each operand from memory. There may be more than one. Operands and registers, again, need not be fetched, which would vary the time it takes for this piece of the pipeline to run, but we are making the assumption that it's going to all take the same amount of time, which is 1 clock cycle. Finally, we have an execute instruction, which again performs the indicated operation and stores the result, if any, in the specified destination operand location. And finally, write operand again is just to store the result in memory. Okay? So if we're just doing this without pipelining, we would basically end up saying that in clock cycle 1, we fetch the instruction. In clock cycle 2, we decode the instruction. Then we compute the operands. Then we fetch the operand. Clock cycle 5, we fetch the we execute the instruction, and finally in the clock cycle 6, we go ahead and we write the output, okay, or write operand. And so if there's no pipelining, in clock cycle 7, we're going to go ahead and fetch the instruction, the code instruction, calculate operand, fetch operand, execute instruction, and write output. And then on 13, we would basically do the third one, right? So this is taking, how long actually, here's a good question for you. How many clock cycles would it take to run all 6 instructions, assuming that they all require each of these stages once? Well, each of them is taking 6. And so first one ends at 6, next one is at 12, Next one's going to end at 18. Next one's going to end at 24. Next one's going to end at 30. And 2, 4, 5. Last one's going to end at 36. Okay? So it's going to basically take over 30 seconds, assuming that each of these clock cycles, very slow machine, one clock cycle. Well, let's do nanoseconds, right? So it's going to take 36 nanoseconds to run this, if each of these clock cycles is 1 nanosecond, okay? Now, let me go ahead and redo the same thing with pipelining in the most efficient possible way, okay? The first instruction is still going to take 6 nanoseconds to run. FIDICO FOEIWO. There we go. However, here's the thing. Instead of doing these like this, once we go ahead and fetch the instruction, while we are in clock cycle 2 decoding the instruction, the fetch instruction assembly worker, per se, is not doing anything. He's not fetching any other instructions right now. In fact, he wouldn't fetch another instruction until clock cycle 7. So he's lazy for all of these clock cycles. Well, not anymore. He just got more work to do now, because now he can start actually fetching the instruction for the second one. And how can you do that ahead of time? How do you know that? Well, you can just check with the program counter and see what will be the next thing, PC plus 2 instead of PC, or PC plus 1, if you're currently at PC. And so he can go ahead and do that while we are decoding the instruction. And again, we're making the assumption that they take them at the same time. But that means that by clock cycle 3, while we are computing the operand, the fetcher, let's say he already finished fetching 2, he can start fetching 3. And furthermore, the instruction decoder person already finished decoding instruction 1. So he can start, he's lazy right now. So he can go ahead and start working on decoding instruction 2. So that's good. Okay, one more clock cycle. So now we're at clock cycle 4. Clock cycle 4, instruction 1 just finished computing the operand. And so now it's going to go, now that it has calculated the operand, it's going to go ahead and fetch the operand. So this fetcher is a different fetcher than the other than the instruction fetcher. Because remember, operand fetchers and instruction fetchers are different, because you typically, you don't have to, but again, it would help a lot, and that's why it's done this way. You keep instructions of a program in a different area in the CPU or in a buffer or in a cache than you keep data, right? So instruction register versus like your operand registers, and so data operand, and so you can keep those in different ones, so you can have multiple system buses. And then again, we'll talk about it when we talk about, I guess, with the resource hashers. But yeah, the point is that the fetch operand can be working while the fetch instruction 1 can be also working on the next instruction here, because he already finished with I3. So you can have those two working in parallel. Furthermore, we've got the instruction 2 has been decoded, and now we can compute the operand. So that's going to be working. And the decoder is going to be decoding instruction 3. So you can see that now we're making them all work. Although so far, the CPU is not doing anything right now, because it hasn't been able to get to an execute yet. He's just like, okay, I'm just chilling here. I mean, I'm getting paid. Why not? So next, we are finally going to let in clock cycle 5, the processor is going to finally get some good work in. He's going to execute this instruction because we have finally fetched the operands. We know what we have to run because we know the opcode and everything. And we store all those in those latches. And so now we can finally get the guy to start working on something. So we get the execution of the instruction. And because we want to have something ready for the CPU next time, we can also go ahead and fetch the operand of instruction 2, because we're ready for that, because we already computed it right here, right? Okay. So now, while this guy is being fetched, we can go ahead and compute the operand of instruction 3, and we just fetched the instruction of I4, so we can start decoding it. And because of that, I5, we can already start fetching that instruction as well. So as you can see, once each of these pieces or components of this pipeline start working, they never stop working. They're going to be working forever until you run out of instructions, okay? So now, let's go ahead and move on to clock cycle 6. At this point in time, we have finished executing the instruction, so now we got to write it out to memory. Okay, so we're going to do that for instruction 1. However, we just finished fetching the operand of instruction 2, so we can go ahead and tell the processor to start executing that instruction. For instruction 3, we just computed what we have to fetch, so now we can go ahead and fetch that the operand there. Instruction 4, we've just decoded the instruction, so now we got to compute the operand. Instruction 5, we just fetched that instruction, so now we got to decode it. And instruction 6, we're just going to go ahead and start out here by first just fetching it. All right, 7. Instruction 1 is done at this point. We've just finished writing it. So instruction 1 is done. So if we're looking at this machine without knowing its internals, whether or not it has pipelines, the first instruction is going to take us as long as it takes with pipeline that it will take without a pipeline. Because there's no way to speed that up. We can't speed up space and time in the universe or whatever, you know. That is going to take as long. So there's no efficiency gain there. However, in instruction 7, we just finished executing the second instruction, and now we just got to write it out. So we're going to go ahead and do that. And we can also feed in instruction 3 now into the processor. And we can fetch the operand for 4. We can compute the operand for 5, and we can decode the instruction that we just fetched for 6. And now, because there's no instruction 7, the fetch is finally going to be like, whew, okay, I can go take a break now in the sun. Okay? So, okay, the water there is too high. I think he'll drown. There we go. Okay. So, yeah. Finally, he gets a break. So, we finished with this cycle. And so we move to 8. So now 2 instructions are done. So here we see this amazing efficiency gain, because while the first instruction took 6 nanoseconds to run, technically speaking, the second instruction from start to end also took 6 nanoseconds. However, the time it took is staggered. So really, as a person looking at, as an observer, we see that the time between the first instruction and the second instruction was only 1 nanosecond. So we might be like, whoa, the first instruction took 6 nanoseconds. The second instruction just took only 1 nanosecond to finish. Because that's what it looks like to us because of the power of pipelining. So while pipelining does not speed up the time an independent instruction takes to run, it speeds up the program as a whole because it basically allows it to be working on multiple instructions at the same time. So make sure you don't sort of misinterpret this. Pipelining allows you to speed up your programs, absolutely. However, the speed up there, assuming that each of these take the exact same time to run each step, the fastest you can get on the speed up is for every clock cycle to finish an instruction. You cannot finish 2 instructions in the same clock cycle with an individual pipeline. Now, if you're running parallel pipelines, parallel processors, different story. But with an individual processor with just one pipeline, the fastest you can go is finishing an entire instruction in 1 clock cycle. However, the only reason that it looks like things are finishing in 1 clock cycle is not because they're taking 1 clock cycle to run. They're still taking the 6 nanosecond clock cycles, which they would take even if you were not using a pipeline. The only reason it looks like you're finishing faster is because things are working in parallel behind the scenes, because you have the fetcher that is always working instead of waiting for each new instruction to fetch. And so you always have the fetcher here working, here, 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 while other parts of the pipeline are running other pieces of this. And so it's still taking 6 nanoseconds for each instruction to run. However, to you, it looks like it's taking 1 nanosecond. So hopefully it's kind of makes sense to you that the more instructions that are pipelined, the less that matters that a first initial slow run before the pipeline fills up. If you only got 3 instructions to run, your speed up factor is not going to be that great. Actually, it'd still be great, but not going to be that great, because, you know, without pipelining, I moved this. Without, let's say 1 instruction. 1 instruction will take 6 nanoseconds. And we'll say with pipeline, without pipeline. Maybe the other way around, actually. So without pipeline, with pipeline. Let us say that without pipeline, one instruction takes 6 nanoseconds. With pipeline, one instruction is still going to take 6 nanoseconds. You can't speed that up. However, 2 instructions without pipeline will take 12 nanoseconds, basically 6 plus 6. Here, it's going to take 7 nanoseconds, assuming that each piece of the pipeline takes the same amount of time to run. And you can, there's no problems, which there will be. But again, this is the ideal scenario. Okay? How do you achieve this? Well, you have to find out how much each independent piece is. And if each independent piece takes 1 nanosecond, then you're just going to say 6 plus 1. Okay? So you have to know that information to be able to compute this. You have to know how many parts there are in the pipeline. So there's a 6-part pipeline. 1 nanosecond each. Okay? So 3 instructions without pipeline will take 18 seconds. 6 plus 6 plus 6. With a pipeline, 8 nanoseconds. 4, 24. 30, 10. 36, 11. What kind of speed up factor are we looking at? That's a 3 times speed up factor there. Over here, this is actually over 2 times the speed up factor, right? Here, it's a little bit under like 1.8 or whatever 12 divided by 7 is equal to. That would be your speed up factor, right? That's how I'm computing it. I just take 30 divided by 10. I could take 12 divided by 7. And if you go ahead and compute that highly advanced computer computation, that I'm going to use my arithmetic logic operator in my computer right now, also known as with the calculator, to get a 1.71 speed up factor. Okay? However, there is no speed up factor there. Okay? There's just 1. Okay? So, this is great. In fact, let's go ahead and finish this just so you see what the rest of this would look like. So here we will finish instruction 3. As you can see, 3 instructions takes 8. That makes sense to what we had down here. And then I guess I'll go ahead and fill up the rest now without talking. But I hope this has made sense now versus just looking at the final drawing. Because the final drawing, you might see it and be like, huh? But hopefully now you see. Okay, so we can see there that 11 basically is for 6 instructions, whereas it would have taken 36 seconds. So you can see there how many instructions we did in less time that would have taken us to do 2 instructions. So this, of course, is ideal scenario. But now, let me propose to you a more realistic scenario. But in pieces. We're not going to go into the hardcore realism. We're going to go slowly. First things first. All the instructions don't take the same amount of time, right? What's going to be the slowest instruction here? Probably one of the fetches. So let's say that experimentally, we compute the slowest instruction here to actually take 2 nanoseconds. So we say that maybe it turns out that the fetch operand is the slowest one, because while the fetch instructions are typically like direct addressing, fetch operands might involve pointers. So that's typically going to be the slowest operation in the system. Okay? So let's say that those actually take 2 clock cycles to do. Okay? On average. They could take more. Oh crap. I only had, let me I need more of these charts. Okay, so all right. Good enough there. Okay, so let's just say that that's going to be the slowest one. So all the other ones take 1. You know, again, that's a little bit hand waving, but let's just say that they did. But there's one of them that's slow. You know, that's the assembly line guy, probably the girl who's putting in the engine in the car. You know, that's actually probably the hardest part. You know, because I mean, putting the wheels is not too bad. Putting the steering wheel is probably not as bad. Painting the car, Well, I guess if you just like spray all the paint, not caring about it, you could do it quickly. But putting the engine is probably the hardest part because they gotta like hook everything up in there and whatnot. But maybe the painting in the engine is gonna be the hardest part. Okay, so we're gonna say that the fetch operand is going to be that painting process. Okay, and so how is that going to affect our pipeline, and how is that going to affect our speed up? Okay, well in that case, if we were to run this just sequentially, you know, and again, let me just copy this a couple of times. We want to use this like 40,000 times today, so yeah, okay, there we go. So we got our pipeline, you know, fetch instruction, decode instruction, compute operand, fetch operand, but that takes twice. So we have an idle here. We're just waiting. We're just waiting for the fetch operand to finish. One way to draw is just to do this with the idle. Another way is you could just merge these two things, but this might be misleading. So I think a much better way of explaining this is just to put the word idle here. If you're dealing with RISC assembly, they use the no op operation for that, which is basically just feeding it nothing, just like, because the operators always has to be working. It has to always be computing, and so you can't just be like no computing now, because it's like it just doesn't understand what that means. It's like, what is not working? I'm used to working every day. And so basically you feed it a no op, which is it's work, but it's just nothing. It's garbage basically. So yeah, so you feed it. If it's a RISC system, you put a no op there. If it's not, you put the idle. So actually, yeah, let's just throw in the no op in there. I'm not familiar actually with that term. So if we got like nope, basically just chilling there, because it takes two, and then finally, you know, it finally gets it, so it executes the instruction, and then it goes ahead and writes the output. Okay. Now, if this was a sequential thing, at that point, you know, it took 7 nanoseconds to run one pipeline, or sorry, one instruction, and if it's not pipeline, then here we start the second one. And so you go there, FO, we got a no op, then we got EI, and then we got WO at 14. So 2 instructions take 14, which makes sense because 7 times 2 is 14, right? Okay. However, we're going to pipeline this. So we pipeline as we did before. We start out the instruction there, and then this goes fetch instruction there, and then it goes fetch instruction here per se. And then CO, FO. Oh, no, sorry. DI. And then we got CO, DI. And then here, we have an issue. We cannot start fetching an instruction on this line because fetch instruction is still fetching instruction 1. So we're like, stop. The assembly line has to halt. It can't work ahead of time. You might be thinking, well, maybe I could CO here, right? And possibly, depending on how this thing is designed, you could. But more than likely, we don't want to because the CO has not handed off what it computed to the FI. And so it's just stuck there. And because of that, it causes sort of a chain reaction. Because then the DI can't hand off to the CO, and therefore the FI cannot hand out to the DI, because the DI is still doing the it still has this decoded instruction, but it hasn't been able to compute the operand, because the compute operand is busy over here because it's waiting to give it to the fetch operation, and the fetch operand is still waiting for actually this one to finish because it takes twice. So it causes an entire chain reaction that halts the pipeline. Like that. But only for one. Because then finally here, we can go ahead and call this fetch operand there. However, in this one here, we have the same issue. The fetch operand there has to basically idle for 2 to be able to fetch that. So while this one can go ahead and finally do the CO because this has been passed here, you know, different color here, maybe. So while this one has already passed it up to this one, it can do that. It can't run the FO yet because it's waiting for that one to run. And then over here, the DI can finally run, which means that the FI can run. However, we can't do the CO because the CO is waiting. And so, essentially, these are all kind of stuck as well. Okay? However, this can happen. The right operand can do just fine their job. It's not connected to the other ones. But the execute instruction, you know, is kind of stuck as well because it's waiting for this one to finish. So finally here, it can execute the instruction, which means now this guy can call FO on the next one. And because CO is free, now DI can hand it over to CO, and FO can hand it over to DI. Okay? And so, as you can see, the pipelining is breaking down a little bit. For the next instruction here, we're going to have a WO here. And then the FO here is going to basically not be done yet because it's still waiting to process because it takes 2 of them, which means that it kind of stucks everything beneath it. Oh, here we had an instruction 6 as well. So instruction 6 gets to finally run here. And then it's still kind of just waiting. It's like, oh. So as you can see, now instead of being able to run one instruction at every second, once we hit that no op, it slows it down to 2 instructions. And similarly here, if I go ahead and fill out the remainder of this chart, EI will run here, and then WO would run here, and then FO runs here, and then we got a NOP here, and then eventually, what's after FO? Fetch operand, execute, yeah, execute instruction. And then here we get to the CO. But here's a NOP, so again it gets stalled. And then here we got DI. And then we get a CO here. And then this becomes the FO. The FO starts there, okay? So really, we only finished 2, 3, and we would have finished another instruction here 4. So, because the slowest thing in our pipeline takes 2 clock cycles, once we kind of hit that issue with the pipeline the first time we hit the FO, it slows down the pipeline, and so we will not see an output every clock cycle like we did before. We'll actually see it every 2 clock cycles. As you can see here at 7, 9, 11, and 13. So by that pattern, I hope you can see that instructions 5 and 6 would have finished at times 15 and 17. Okay, I'll leave it to an exercise for you to fill out these last 2 lines here, but it should give you 15 and 17. And so the speed up factor, let's go ahead and calculate that again. So we would have gone from, without pipelining, it would have been 7 here, 14, 21, 28, 35, and then 42. Speed up factor, again, you can never go faster with pipelining, so the first one's still going to take the same time with or without pipelining. But then we go to 14, to 21, to 13, 35. So they're still really relatively nice. Like, we're still going 2 times as fast here. And then here we're going a little bit over 2 times. But let's see at the 42 how much that is. So 42 divided by 17 is 2.4 speed up factor. So, you know, this is not as nice as, say, 36 divided by 11, which is, I believe, 33.3. But let me just triple check. Yeah. Oh, 3. Oh, wait, 36, not 33. Sorry. 36. So that would be 3. Yeah. Okay, so it's almost 3.3. 3.27, which is about 3.3. So, you know, 3.3 versus 2.4, it's not as good, but it's, hey, it's still twice as fast. I don't know about you, but like, if something's going to take 10 years to run and it only takes 5, I'll take that, you know? So the easy way to compute this is as follows. this is the idea of a bottleneck, right? Or the weakest link kind of thing. The weakest link in your pipeline is going to be the slowest piece of the pipeline. That's going to determine how quickly you can finish instructions, because it doesn't matter if you got 6 pieces in your pipeline and 5 of them take like a micro or nanosecond to run. They take even smaller than that. You know, they finish pretty much instantly. But then you got one heavy, slow piece of the pipeline that takes 10 seconds to run. Then your whole pipeline is going to end up taking 10 seconds to run for each of them. Okay? So really, pipelining is useful when each piece is basically about the same speed. But if there's one piece that is extremely slow, then it's going to be useless. And so what you need to do there is you need to figure out why it's slow and then pipeline that individual piece into multiple pieces ideally. Or figure out other ways of solving it. Such as, again, in practice in a computer, that's actually going to be your main memory that is requests that are slow. And we solve that by throwing in things like cache and, you know, different buffers and prefetching and things like that. So, yeah. Okay. So I hope that you understand that scenario. Now let me pose to you another scenario. So let's go back to the idea that an instruction takes all instructions are at the same speed. Okay. So let's just say that every single instruction again is going to take 1 clock cycle. So we don't have any slow ones. But I'm going to pose to you another possible scenario that could be an issue for our pipeline system. Okay. And for that, I am going to go ahead and go back to doing this. And I'm going to be pipelining out the first 3 lines of this system. So instructions 1, 2, and 3. Okay. And because of that, you know, let's just say that, yeah, right here actually. We're going to do this until 7, okay? So let me fill up for the remainder of these. Like that, okay? So this is our current pipeline. We are running, we're just executing right now instruction 3. But already in the pipeline, we have instructions 4, 5, and 6. And technically, we had a 7th instruction here. So let's just add in another column. Okay, let's try that again. We had instruction 7. That one we already fetched, or we're in the process of fetching actually. Okay, so this is what we got here. You know, pipeline is working amazing. Life is good. We're getting that really nice 3 times speed up factor in this scenario. By the way, what's the theoretical limitation of that? The theoretical limitation of the speed up factor is going to be how many steps are in your pipeline, and then how much each individual piece takes. So if you got 6 steps, and each one takes 1/6 at a time, then the theoretical limitation would be under 6 times as fast, right? Because you still got to run each of them. And so instead of running one every 6 seconds, you can run one each second. So if you were to do this for like, let's just say 1,000 instructions, that would take 1,000 instructions plus 6 to run. So that would take 1,006. Whereas without pipelining, it would take 6 times 1,000, which is 6,000, right? So you can see how approximately 6,000 divided by 1,006 is just under 6 times as fast. So the limit is going to be basically that, because the more zeros that we add, we're still going to have this little piece here. So this could be like 6 trillion divided by 1,000,000,006. And that basically is like 5.9999999 times. Okay, so that would be the theoretical. So that's also kind of a useful thing to know. But anyways, back to this. Let me drink some water while we are processing these instructions. So we're running these instructions. You know, instruction 1 is like, I don't know, int x equals 5. Instruction 2 is int y equals 10, you know. So instruction 1 is like int x equals 5. Obviously this is assembly, but you know, bear with me here. Instruction 2 is int y equals 10. Instruction 3 has the dreaded word if in it. It says if x is greater than 10. Dun dun dun. The if statement. And so when we execute that instruction, it means we are comparing 5 and 10. 5 greater than 10. And so instruction 3 is technically the if statement. Instruction 4 would be the inside the if statement. And maybe there's a bunch of other code here. Instructions 5, 6, 7, blah, blah, blah. Eventually, after the if statement, so let's say that's instruction like 10, we got some other code. Okay? The problem is, the if statement is false. So we don't do the code inside of here. Guess what? Well, we had fetched here, instructions, or partially fetched here, which was instructions 4, 5, 6, and 7, which was code inside of the if statement, is now all of a sudden useless to us. It's garbage. It's like literally useless. Okay? So like hashtag triggered because we did this work for nothing. This is like the instruction basically says go somewhere else in the program counter and do a different color car, or like make a SUV now. So like that car that you put the wheels on and the engine on and you were just about to paint is no longer needed. So throw it away. Start out with the SUV. So this is what is known as a branch penalty. Okay? And what it's going to do for you is you're going to have to basically stop right here. Full stop. And all of this work, all of this hard work that you had worked so hard to achieve, work hard to achieve, okay, is basically garbage. It's useless to us now. So throw it away. All those fetches, all those decodings, all of that, wasted. So sad. Very tragic thing. But, you know, that's what branch instructions do to us. They break our heart. And so now we do know because, and when do we know that? We only know it after we compared 5 and 10, which is right here. So that's why before that we don't. And so that's why technically while we're figuring out what this is, we are still doing this line, right? But only after that line. So when we get to the next line, we can start writing the output here. But there's no point in doing any of these anymore because at that point we know. It's like we know the truth, the hard, dark truth, that the next line of code is actually instruction 10. And so what do? We accept the cold hard truth that our pipeline is broken and we got to start filling it up again. So we basically have to flush out the pipeline and start up again. And so instruction 8, you know, this is not exactly lined up, but you know, you get the idea. Let me try to line it up. There we go. So instruction 8, you can start fetching because you know you don't give up. You start feeding the pipeline again. So you start fetching instructions 10s, or sorry, here, the instruction to go. But guess what? Now you got yourself the branch penalty here because the write output, the execute, pretty much every single one of these except for fetch instruction have nothing to do now. You know, so decode instruction, compute operand, fetch operand, execute instruction are all basically without anything to do now. Write operand still has something to do, which is writing basically the one that basically broke our thing, which technically there isn't one for this because it's a jump instruction, so there's nothing to write to main memory. But hey, whatever, you know, let's just say that there was. So maybe you inside of the if statement you trolled the system and you said like if x is equal to 0, you know, you meant to say x equals to 0, but instead you said x equals 0, and you're basically like, oh no, big bug, right? So yeah. Anyways, point is, Oh no. Oh no, maybe I have a pipeline break because now the iPad froze. Hold on a second, guys. Stand by. We have technical difficulties with the iPad. Okay, we're still working on the iPad here for a second. It just froze and doesn't let me move around. I don't know why I decided to just freeze out like that. Let me. I'm trying to see how to force close something. Here, there we go. I think if I just force close, otherwise I'll restart the tablet. There we go. I got it working again. Okay, so I just have to force close the app. Okay, so I guess there you go. That was a pipeline that probably broke, and then it had to be refetched, right? So, anyways, back to this. So, okay, so we are now at clock cycle 8, and we can start fetching the next real instruction because the branch basically said that it's not instruction 4 because it's not the thing inside the if statement. It's actually out after the if statement. So, you know, again, I guess I wrote it really tiny there, but basically imagine we have int x equals 5, int y equals 10. If x is greater than y, then I don't know, x gets 5. Well, it already has 5. So x gets 10. And then see out. Oh god, let's not do IO calls. Let's just go ahead and do more computations. X plus plus, y plus plus. So now we are at instructions 1, instruction 2, instruction 3, instruction 4, 5, 6, and then, I don't know, there's just a bunch of other instructions. 7, 8, 9, okay? So we got 3 more instructions. We can think of something. 7, 8, and 9. So maybe we do, we really do need another variable here, but okay, whatever. We're going to do y plus plus again. We're really bad coders. We don't know how to do like y equals plus or y plus equals, you know. But eventually we figured out and we said that. Okay? So, yeah. There you go. Good enough. And so finally, instruction 10 is actually after the if statement, which might be something like int b gets 5. Okay? And then from there, something like int g gets 10. And then like g plus plus. So this is 11, 12, and 13. Okay, and so on. So basically, come on, 13. I don't like how the 13 looks. Basically, you know, that means that the whole work of 4, 5, and 6 is just wasted here. You know, hashtag triggered. Okay. So now, you know, we start the pipeline again. So we do the fetch, and then we decode the instruction, and then we compute the operands. And while this is happening, we can go ahead and fetch the next instruction and decode it and fetch. And then from there, we can fetch operand, compute operand, decode instruction, fetch instruction, and so on. Then we can execute the instruction, and then we can write out. So the effect that it has on the pipeline is that the penalty is going to be while you fill out the pipeline again, which is basically going to be, I mean, depends on where the pipeline breaks. Because the pipeline breaks typically when you execute the instruction and figure out that it's a jump sequence. You might still have one more thing to do afterwards, which is your write. And so if we notice here, the next instruction to finish the pipeline was at time 13. So there was from 8 to 13. So that basically took 5 nanoseconds. And because each of the instructions takes the same amount of time, you can see that it's not a full complete and like, you know, we lost everything all 6 seconds. So the pipeline wasn't completely utterly useless. We still had one piece gain because we have the right operand instruction here is happening at the same time as the fetch instruction here, because at that point we know. But if for some reason, again, this doesn't happen, it always happens, I think, in the instruction, pretty much will always happen in the execute instruction. But if it happened in the right operand, somehow the thing got broken at that point, then yes, we would have to do this. The full pipeline will be empty and it will take the full 6 seconds. So really, if we were computing the time, the first one takes 6 seconds, the next one takes 1, and I think how many are there? 6, 1, and 1, yeah. And then the next one's gonna take 5 seconds. This is basically a post-branch refill pipeline. And after that, assuming that there's no other branchings, then they'll go back to taking 1 second each. So it's only a temporary problem per se, okay? But you still have the efficiency gains as long as you don't have any other branches. And if you have another branch, then you can throw in another 5 second computation time, you know, or clock time added to that. But again, ideally, the majority of the instructions are going to not have any jumps, and they're going to be sequential. We are taking advantage of the idea of principle of locality of reference in terms of spatial locality in this case, because we assume that the next instruction in the code or in the program is going to be the next instruction to be executed. So like instruction 14 will go after instruction 13, and instruction 16 will go after instruction 15. We expect that. Jumps in our programs, which are if statements, loops, procedure calls, and those kind of things, go-to statements, I guess. Those are all of the ones that are going to break this idea, but they don't happen as much. And if they do, there's still more non-jumps happening than jumps, okay? Go ahead and look at your IAS program that you made and try and count, you know, look at the code and see how many if statements you have, how many function calls you have, and then how many regular lines of code you have that are one after the other. And you'll notice that, yes, you know, we do have if statements. If we didn't, code would be very boring, but there's still very few compared to the regular things. In addition to that, we're going to talk about some of the ways that we can try to avoid this issue. What's one of the most obvious ways that we could do it? Well, if it's an if statement, and there's only like let's say there's just like an if-else clause, or it's just a pure if statement. Yeah, let's just go with this one. Just a pure if statement. Okay, if it's just a pure if statement, then it's really a 50-50 chance, you know. We've got this line of code potentially to run next, and then which means we can pipeline all of the stuff beneath it. Or it's instruction 10, which is, what was instruction 10? We never had instruction 10 in there. Interesting. Okay, well, we'll say int x, or we'll say that int xx gets 10. Okay, so this could be the other option, that this might be the next line of code, right? Which means that we have to pipeline the stuff beneath it. So with this scenario, ideally, you know, the easiest solution that you can think of, you know, modern programs require modern solutions, is that you can just have 2 pipelines. You know, if you're gonna, if you potentially are thinking that you might run into a situation where you may run into a jump statement, then you can go ahead and prefetch both pipelines. However, this makes a dangerous assumption that you know that the pipeline jump is coming, but you don't. You don't, because you only know after you execute it. However, technically speaking, when you are decoding the instruction here, you can see that it's a jump instruction. You know, it's a go-to statement. It's a, well, in assembly, it's pretty going to be a branch or jump. So if you see something like that, then you can see ahead of time where those jumps are going to be. Where would you see that? Not in the decode, but over here, right? In the compute operands. That's where you can compute and figure out where those jumps could be if they happen. So it is only then that you could actually figure out, oh snap, okay, we got to go with each of these. So you can still be doing your regular, you know, spatial locality by just pipeline the next thing. But at that line, you can also then start another pipeline with wherever the other possible place to be is. You're still going to have a little bit of a loss because you can see there's 2 instructions that happen before we figure that out. Or technically 3, I suppose. Yeah, 3. So you're still going to have a loss, but it's going to be a loss of 3 versus a loss of 5. So instead of seeing this as 3s, you would see them as 3s. So which is better. And again, at the end of the day, computing is not just about trying to figure out the ideal, but just trying to figure out something better than what we have now, and then slowly chip at the problem to make computers faster and better, right? You don't just invent. It's like you don't just go to Mars. You instead go to the moon first, experiment technology there, and then make baby leaps and then go to Mars. And then maybe then you go to Titan and so on, right? You go in baby steps so that you can learn in the process, right? And that's what happens with computing. We improve in tiny steps, which at the end of the day, when we look back in 10 years from now, it's a great improvement, but that started out with tiny pieces. You don't just all of a sudden, pull out a brand new system that is like 50 billion times better. No, that's not how it works. It's all in tiny experimental steps that start out at places like universities where the research happens and Intel and research centers. So yeah, that is basically one of those solutions that you can do, right? This is known as branch prediction. And for branch prediction, there's a couple of different things that you can do. So let's go ahead and let me pull out in the book. They have or here actually probably pull out maybe in the PowerPoint. Maybe they have a slide on this. We still got to talk about pipeline hazards, but I'm going to skip that. And so let me switch over to the PowerPoint. Okay, so multiple streams. We still need to talk about hazards, but we'll come back to that. So multiple streams. So a simple pipeline suffers a penalty, basically choosing which instruction to take. One way to do it, which is what I said, is to allow the pipeline to take both versions. The drawbacks, again, more circuitry involved. Contextual delays, don't worry, I'll explain that in a minute. But eventually, it's just more work, and it's tricky. But even so, trying to figure out how to do it, it's not easy. And IBM 3691 started out with the approach which is what I was talking to you about. But other ways that you can do it is you can also remember where you've been already. This one right here, this is like, there we go. So one of the ways that you can do it is there's 3 sort of ways of handling this that are just like hard-coded per se and not dynamic, static per se, and 2 that are dynamic. So the 3 is always assume they're going to take the branch that you've never taken before. So that would be like, again, if you've never gone to, if you have not, if you hit an if statement, which one have you taken yet, or which one have you not taken? That's kind of tricky. But just assume that you're not going to go into the if statement, for example, or assume that you are going to go. So basically, predict whether you've never taken it or you've always taken it. Okay. You can also just assume by the opcode. So, like for example, the book says, and I will take that with a grain of salt, that historically, when you were looking at code, over 50% of the time, if you write an if statement, you're actually going to go into the if statement, like into the if clause of the if statement. 50% of the time. More than 50% of the time. So they're claiming that the way that people write code, more people write code to enter the if statement more often than to go outside. So what would be an example of that? An example of that would be like, if you want to check something, you go in it after you check it. And a counterexample would be, let's say that you want to check for null. And if you check for null, then inside of the if statement, then you see out an error and then bad things happen. So you very rarely are actually going to go into the if statement. That would be a counter argument where I would say that's not true. So it really depends on how you write code, really. But they're saying as a whole of civilization of coders, I suppose, they're saying that we write more code that we actually enter into an if statement. So I'll let that to the user or to the listener to refute or agree with. You can leave a comment on that if you want. So that's one way of handling it. Another way is to be dynamic about it, which is basically to remember what has happened. So like, suppose you're going in a loop code. Loops typically loop, X amount of times, and then they go out. How do you know it's a loop though? The computer doesn't know, because it's just in assembly, it's just jump instructions, right? When you write loops in assembly in 218, they look like if statements, they're just jumps. You know that it's a loop because of the way that you write the code, but the computer doesn't know that. However, it can start to sort of detect that if you're running the code like 1, 2, 3, maybe by the fourth time it's like, hey, okay, I'm running the same, I'm going to the same location every single time, which is to the top of the loop code. So then it keeps that in the branch history table, and so it basically starts to see that, okay, we haven't taken the one that goes after, so more than likely I'm going to just go ahead and assume that he's going to loop again. And it's ideal because that means that every time you loop, you're not going to have that branch penalty. You're only going to have one branch penalty, which is probably when you get out of the loop. That final time, when you finally do get out of the loop, more than likely by then the computer just assumes you're going to go in the loop again. But it's okay, because really, if you're looping 1,000 times, it's better to have 1,000, maybe to have 950 times where you don't have a branch miss because you actually, the computer already realized that you're looping, and then at the end of the loop you have one miss. Okay, that's better than having 1,000 misses, because it always just assumes that it's like, okay, that must be the last time he's looping. There's no way he's going to go in again. Oh, I guess he won again. Well, this would be really, really the last time, right? So those are basically the ways of taking. Another way of predicting it is like, take the one that has not been taken yet. If it's an if statement, it might be like, well, last time we took it, so maybe this time we won't take it. So I'll leave it to you to read on those and kind of find more about it. But ultimately, you might don't just be like, oh, well, we can do machine learning on this. No, guys. Remember, this is happening at the very, very basic level of a computer, like the lowest possible level. This has to be something that has to be computed quickly, okay? Yes. Could I do some super deep analysis of some code and make a really good prediction on what's going to happen in the next line of code? I probably could, but I could also take 10 days doing that. I could go, you could give me some very big piece of code and then tell me a line that you're at, and then tell me what is the next line of the code going to be. And then I can go ahead and analyze that code in detail and come back to you 10 days and be like, okay, I think 99.9% of the chance that the next line of code will be this. You can do that. That's useless. That's literally useless. I could have picked out 50 different variations of pipeline in that time. So there needs to be something that you can make that decision on the fly immediately. Okay? So your brand prediction is great, but you can't do it at the cost of time to actually compute the prediction. So you have to do, that's why you have to go, keep it simple, basically. Okay? Keep it simple, because otherwise you lose the whole efficiency purpose. In fact, that's something that I didn't quite talk about, but it is mentioned in the book. Pipelining itself adds overhead to the system. An assembly line adds overhead to a system. The time it takes, if we go back to the car example, the time it takes for the conveyor belt to move from one guy's workstation to the next workstation is time lost versus one single person building the car on their own. It's possible that person can very quickly switch between putting in the wheels to putting in the steering wheel to painting the car to putting the engine and all these things. So it's always going to be faster to not use pipelines if you're just doing one single instruction. However, the loss in efficiency by introducing pipeline is very tiny in comparison to the amount of speed up that we can get with pipeline. So again, the same idea behind cache. Cache adds overhead time, and it also adds more circuitry. And sometimes when you have cache misses, it makes things even worse. But that's very rare, because the majority of the time it's going to make things faster. So in overall, when you're looking at the general average of the thing, it's going to be way, way faster. Okay? So same with pipelining. So remember that concept in computer science, but also in general. That the more things you make complicated with the idea of making things faster will potentially slow things down initially, but at the long run will be much faster. And that is why it is there. Okay? Smart people computed these things and basically said, yes, pipelining will make things faster in the long run. And so what else do I want to say about branch prediction? I think that's it for branch prediction. Oh, the loop buffer. The loop buffer is, they mentioned the thing about the loop buffer in the book. It's a very tiny piece of memory that can actually kind of help out with specifically with loops and things like that. It also can target a few addresses ahead of time, and it's a pretty nice idea. So check it out, read it, leave a comment on that. And okay, so now I want to change topics here and talk about hazards that can come up with pipelining that you might not be thinking about. And Oh, here's some nice little graph of speed up. But I showed you how to do the speed up with the staging, right? I did a little computation. So this is what it would look like graphed. You can see that the speed up kind of wears down as you reach the theoretical limit because of the number of stages, right? So, for example, if you have 20 stages and each one takes, and they all take the same amount of time, you know, you can have you can have a maximum speed up of like 9.999 in the case of 10, right? So it could never go higher than 10 potentially. So the more instructions, the more speed up. If you're just running one instruction, then it's slower essentially because of the extra overhead, right? But by the time you get to 2 instructions, you're already like speeded up like fast. So pretty quickly, pipeline becomes very good. But anyways, so pipeline hazards, okay? There's 3 pipeline hazards that we need to talk about. They're resource hazard, data hazard, and control hazards, okay? And they will talk more in detail about these things in the 370, but I do want to introduce them to you. So let's start out with resource hazard, okay? Let's look at our pipeline yet again, the one that we did. Let's look at the one that's prettily drawn here, okay? So we have a couple of main memory accesses. Forget about the cache for a second here, okay? We have fetch instruction, we have fetch operand, and we have write operand, right? If all of these things are stuck in main memory, they all are potentially read or writes from main memory, which means they have to use the system bus, right? If they have to use the system bus, then that's a resource. And let's say we only have one wire to communicate with main memory. Well, they can't all happen at the same time because that wire is busy. And so the pipeline would potentially break because now you can't stack for example, a fetch operand with a fetch instruction like you have here. You can't do that because they both require the same resource, which is communicating with main memory. Even worse is something like this. You have write operand, you have fetch operand, you have fetch instruction. Basically, once your pipeline is full, is right here. That's what, actually here, in this one too. This one here, clock cycle 8 here is when your assembly is working at its maximum speed, the pipeline, because all the pieces of it are busy, right? So they're all working at the same time. And that's good. That's how you get that speed up. But if they're working at the same time, and they're all using, oh, actually, I guess 6 is the fastest here. From 6 and on, it's the fastest, because already there, we got everything from the write operand, which is the last part, to the fetch instruction. Yeah, so from 6 and on, that's when you really have that maximum speed up. Okay? However, because they're all working at the same time, write operand, and fetch instruction are all potentially talking to main memory or to cache. This causes issues because, again, you might be limited by the number of communications that you can have concurrently with a resource like main memory. And so write operand may have to wait for fetch operand to work, but then that is going to slow down that pipeline piece. Or fetch instruction may have to wait because fetch operand is working, right? Ideally, in this scenario, this guy might be better to wait right now because these guys are more important because he's done, kind of. But then it's going to slow down from here and on. So you can see how resource limitations may screw up with the pipeline because, like, imagine that the example that I could tell you is, let's go back to the car. Okay, let's go back to our 4T motor assembly line. Let us say, where's my pen? Oh, here we go. Let us say that the guy to put the wheels here requires that one tool, you know, the little like screwdriver, what do they call it? Drill. The little drill that, like, you know, tightens the bolts in the wheel, right? You know, you tighten those bolts. Let's say that this guy's using it. Okay? But guess what? This guy's got to put the wheels on the other side. He can't do that because he's using this tool. And he needs the tool to be able to do it because he doesn't want to do it with his hands because the union doesn't let him do it, okay? So now he's got to wait for him to finish and then use it. But then guess what? When he gets a car, he's got to wait now. So there's a problem. So ideally, you give him both drills to be able to work at the same time. Otherwise, this completely breaks down that part of the pipeline because they can never be working at the same time. So they might as well not be done, but they might as well have one person putting all 4 wheels, because if they both need a drill, then you're never going to have any speed up. You know, if all of the pieces of the pipeline require, for example, a wrench to be able to do their job. Like they all require a wrench. If there's only one wrench, then the pipeline is completely useless because the only one can be working at a time with the wrench, which means that you might as well just not have a pipeline at all. That's the worst case scenario. If they all use the same resource and only one can use it at a time, then your pipeline is garbage at that point. It's like GG's, not easy, don't pass go, don't collect. Okay? So that is almost a resource hazard, and typically the problem there lies from being able to access main memory. So what are the solutions to this? Well, going back to the picture here of the entire pipeline, fetching instruction and fetching operand, if they're happening at the same time, which they start from here and on, what you can do is you can split that to different locations so that they don't conflict, which is why in cache you typically have a section reserved to instructions and a section reserved to other data and operands, right? And so by doing that, you can avoid this problem by ensuring that you can have access happening at the same time. Also, if you are dealing with things that you have to access from memory, you can add more buses, more lines, basically, wider lines. You can communicate more things at once. That way, you can have the write operand and the fetch operand. You know, one of them is going and one of them is coming, so hopefully you can have them both working at the same time. And then have something in main memory to have a buffer to be able to receive and work. Because, I mean, the main memory can only do one thing at a time, right? So, but, you can prioritize the fetching and save the writing for later. Although that's going to cause another issue that we'll talk about in a minute, but we're not there yet. Okay? So those are going to be potentially ways of solving resource hazards. Basically, if you have a resource hazard, solution is add more resources. If everybody needs a wrench, then go buy more wrenches so that people can be working at the same time. If the two people putting in the wheels need to have drills, and you only have one drill, solution, get another drill. Easy as that. However, of course, that means money. And money is money. So therefore, you might be like, well, it's expensive, so I will sacrifice some speed up to not have to spend more money on another drill. Or in the case of here, system bus, go buy the cheaper motherboard that has crappier system bus because it's cheaper, So, yeah. Okay, so that is going to be your resource hazards. Another problem that you might run into, and here's, I guess, an example of a resource hazard with the fetching. The fetching can't happen because the fetching operand is happening and the fetching instruction is happening, so it has to wait. So you can see the idling here. Source operand memory. But anyways, so the next one is going to be data hazard. And this one they really will talk about in detail in 370. So there's three kinds of data hazards. They're read after write, write after read, and write after write, which are known as true dependency, anti-dependency, and output dependency. And basically, let me give you a situation where this is the big problem here, okay? We have the following assembly code. You are adding EAX and EBX. And if you remember your assembly, which I think I do, but you guys can correct me in the comments if I'm wrong, when you go ahead and add EAX and EBX, the result of the addition is actually stored in EAX. And because it's stored in EAX, the next line of code here is to take ECX, subtract that from EAX, and then I think store the answer in ECX. Okay? Here's the issue. With pipelining, you might pull out the older value of EAX to use for the subtraction instead of waiting for the addition to happen. That's really bad. That's like if you write a piece of code that says int x equals 6, x plus plus. If x is greater than 5, do this. But here's the thing. If you don't wait for the x plus plus to happen, then the if statement is going to be wrong because it's going to have the old value. And you don't want to have old values because that's going to break coding in general. Like, that's going to be a pain. So because of that, you basically have to wait for the previous computation to finish before you can continue and on. So again, imagine an example where you are reading in a value from a user, something like C in X, and then you're going to say if X is greater than 10, okay? you got to wait for the reading to happen before you can execute the line beneath it. With pipelining, with the way that fetching works, if you just do the pipelining system that I showed you, you don't care what is in X. You fetch it ahead of time so you're ready to go. But that's a problem, because you're fetching the old value of X. And that's bad, because then you're going to be doing math on a wrong value. So what do you have to do? You have to wait. You have to wait for the computation to finish on the resource that you're working with, that variable, before you can continue the pipeline. And this is showing that example here, because what happened is, you start out with here, you fetch this instruction, you don't know what it is yet, you don't know that it's add yet, you don't know anything at that point. You just fetch it. Clock cycle 2, you decode it. You already start fetching the next instruction. You don't know what it is either, but you do that because you want to have your pipeline working. Eventually, you decode it and you see that it's an addition. You don't know yet what addition, who, what, where, why, how, when, whatever. You don't know anything. You go ahead and you fetch the operands now, so that you can see what it is that you have to do. Okay, so you see that it's an EAX and EBX. At that time, over here, you're decoding the next instruction, which also says that you are subtracting EAX from ECX. And you're like, oh snap, I can't take EAX's value because it's being currently used here, and I'm going to write the answer here. So this pipeline just halts, and it has to wait for the new value of EAX to be stored, so that then it can go ahead and fetch it, which is fetching the operand here. So first, you have to execute the addition, write up operand, which is in this case writing it to the register, and then because it's written, then you can fetch it. But this will be the same thing if this was writing it in main memory, because you have to wait for it to be written to main memory to then you can fetch it from main memory. Because you have an idle here and the DI is kind of busy because it decoded the instruction but it can't fetch it, you can't call DI again. So you waste, or you have your no ops or your idle here until you are able to move on to the fetch here, which then you can do here. And similarly, you can't fetch anything else because you're still waiting on this one. So as you can see, everything slows down. So you have a whole line here of idles. Eventually though, once you pick up the pace again here, because you assume that these instructions have nothing to do with the previous ones, so the pipeline recovers at this point and you have +1 on each of these. But here, as you can see, there is a +3 difference here. And that is because you have to wait for the EAX value to update. This one would be considered as a read after write. Yeah, an instruction modifies a register or memory location. A succeeding instruction reads data in memory or register location. Hazard occurs if the read data takes place before the write operation completes. So again, the hazard is if you try to read EAX before the addition writes the answer to EAX, that's a problem because you're reading old data. Okay? If that doesn't make too much sense, don't worry too much about that. Again, they will focus on 370 when they're talking about parallel programmings and race conditions and all these beautiful things. Okay? So ultimately, the idea is simple. If you're using some data, but you're depending upon the previous thing, you can't fetch it again. It's like if at the end of this car you're building, only then do you find out that do you need to use that information to get the next car, then you can't do anything until you get the information. So you gotta wait, because otherwise you're gonna use it on old information, which might be wrong. It might be a different color. And so that's gonna be read after write. Write after read, or anti-dependency, that one is basically when a hazard occurs if the write operation completes before the read operation takes place. Let me think about this for a second. Occurs if the write operation completes before... okay. So that one is a little bit not easier to see with pipelinings, but like... So suppose that it's kind of like the inverse, if you were supposed to read an old value, so let me give you some C++ code maybe. I think that'll be a little bit easier to understand. Or do they have actually a picture maybe for that one? Because then I could use a picture. No, they don't. Okay, so let me give you an example. I need to change this chair. It's squeaking. But I tried to buy a new one, but they're out of stock because of Corona. So yay. Okay, so let's say that you have the following code. So the first one, the read after write, you know, you can basically say something like cnx, and then if x is equal to 10, okay, and then maybe int x has 5, okay. So this one, it should be obvious that you definitely need to finish the reading here before you can run the if statement, right? Okay, so the write after read is going to be, for example, if you have the following line of code. So int x equals 5 if x equals to 5, x plus plus. Okay? In this case, if for some reason you actually do this line of code before you actually finish doing this comparison, then you would get a wrong answer, right? Because you get x equals to 6 and then 6 is not equal to 5. So that would be kind of the, I know it's kind of weird, but this makes more sense when you're doing about parallel programming. So if you got two processors, you know, that are working on this in this program, and then somebody else writes to it before you were supposed to be able to pull the information from it, then that would happen. So really, this will be easier to understand it when you're doing parallel programming, okay? But basically, if you're writing to something, but you were supposed to read the old value beforehand, then you're gonna run into this problem, okay? Maybe, for example, a loop counter could be something like this. If you're supposed to read, if you let's say, yeah, that's actually not bad. So the difference between I++ and plus I, yeah. So with you expect I in this scenario. Let's say I is equal to 5. Okay. If I is equal to 5, and I go ahead and I set two variables here, which I'll call j and k, what do I expect j to have here? I expect j to have 5 here, okay? And then in the line beneath it here, I expect k to have 7, right? Because what ends up happening here is j gets the old value of I before the plus happens, right? Whereas with k, you first increment I, which already has 6 from the previous line, which becomes 7, and then you pass it. So k is going to have 7 in this case, and j is going to have 5. If you run the same code backwards, so if I have x and y, and I'm doing plus I and I plus, and then again int I has 5, in this scenario here, x is going to have 6, and then y is going to also have 6, even though I would have 7 inside of it, okay? That's pre and post increment, okay? So a write after read or anti-dependency would be if you coded these backwards, basically. So like if when you were coding I++, you coded it so that you would increase the I to 6 before copying over to j. So here you copy it first and then you increase I to 6. But if you coded it so that it's always increasing it first, like you were overloading an operator or something and you coded it so that it first increases it to 6 and then copies over to j, that would be a write after read anti-dependency problem. That's actually, I think, the easiest example to understand, okay? So that would be like if you flip these backwards, okay? Vice versa, read after write. The read after write is basically where you are doing a read before the write operation takes place. So, suppose that when you were coding I++, you coded it so that it worked like, when you were coding plus I, you coded it like I++, where it reads the value of I first into k and then does the increment. If you coded it out backwards, then that would be a read after write true dependency that data has it, okay? So just remember your pre and post increments, okay? As an example of the difference between those. Finally, we have write after write. That one is also known as a output dependency. In fact, here let me go ahead and let me write these back. Let me write this in the notes here, so I don't, because I think I actually kind of like this example. So if I ever have to teach this class again, I'm gonna remember this. So this would be I++. Basically, would be to backwards. So if coded backwards would be a write after read. And then I++, or sorry, ++I, if coded backwards, so I++ would be read after write. Okay? Like that. Okay? So finally, write after write is basically if write operations take place in a reverse order of the intended sequence. So basically, if you have two writes, so like for example, let's say we got int v equals 10, and then you have b++ and b++. In this case, you expect us to have 12 afterwards, right? However, it doesn't really matter which one you do first because they both do the same thing, right? They both just increment. Okay? Well, suppose that this was b times equals 2 like that. Okay? So in this case, this would make it 11 and this would make it 22. Right? However, if we run them backwards, we'd actually get v times 10 times 2, which is 20. So if we did v times equals 2, and then we did v++, starting out with v10, we would first get 20, and then we get 21. So of course, these are different numbers, completely different numbers, 21 and 22, different numbers, right? So order matters, right? If for some reason you actually end up flipping the order, so like you execute this before you execute this, then that would be a write after write problem. And again, that really doesn't happen. You're like, why? Why would I even do these backwards? This is weird. That doesn't really happen normally with pipelines, I suppose. But in 370, when you talk about parallel programming and race conditions and all these things, then it could happen because you have two processors writing to the same register, for example, and you intend one of them to write before another one does, and if they both write at the same time, then it screws things up. Or for example, let's say that there's a 2 in this register. This processor takes it and then does plus plus to it. This processor takes it and does plus plus to it. However, they both take the 2, they're both going to write 3 to it, which is wrong because you intended a 4. So maybe this one goes in, writes plus plus, puts the 3 back, and then you got to wait before this gets a 3 written there. That way you can take that and then return a 4, right? So again, this is what's in your future in 370. But for this class, that's kind of the limitation of what we're talking with data hazards. Again, the only one that really matters for us is going to be the read after write, because that's the one that can actually cause problems with pipelining that are realistic, which are again we have to wait for a computation to finish before we can use that variable in the following computations, which do create these idle scenarios with pipelining. Okay, so I think that pretty much concludes the pipeline organization. Let me see if there's anything else that I wanted to talk about. There's loop buffer, branch prediction. Make sure you read this as well, but still. They do talk about the Intel 8048.6 pipeline, which has those 5 instructions. Definitely read that. They were basically fetch, decode stage 1, decode stage 2, execute, and write back. So do go ahead and read those on your own so that you can get a little bit of insight into the different developments of pipelining throughout times. And then also along with the ARM processors. The only thing that I kind of want to skip to is actually not in chapter 16, but in chapter 17, and it is 17.5, which is risk pipelining. So risk pipelining is a variation of pipelining, but how it works on risk. And I thought I'd show it because it is kind of neat. So this one, okay? So this picture is on page 607. So in risk, you basically have three main stages for, at least for load and store operations, you have three stages. You have instruction fetch, you got execute, which calculates memory address, for example, and then you have the D, which is register to memory or memory to register operations. So IED basically, okay? Not like IED like a bomb. What is it? Explosive device? No, IED like this, okay? And then for register and register instructions, you only have really like instruction fetch and execute, because those are actually stored in register, okay? So you have IE or IED. And so with the pipelining here, you got some examples of some assembly code, or like you're loading into a memory, you know, for example, you got IED, IED, IE for doing this. There's no D here because you're just doing operations on the registers, no memory involved. And then IED, and then that's just a branch. So here's an example of sequential. Now, how would you pipeline this? In a two-stage pipeline, you can go ahead and do the I here and the E, and then the D, you gotta wait because you have to wait for the memories, the system bus to basically clear out, essentially from there, because you can't execute it. Because remember, in the risk, the execute actually, you know, is going to be calculating the memory address, okay? And so in IE stages of two different instructions are performed simultaneously. The two stages of the pipeline are an instruction fetch stage and execute stage. The second instruction can be performed in parallel with the first part of the execute memory stage. However, the execute memory stage of the second instruction must be delayed until the first instruction clears the second stage of the pipeline. This scheme can yield up to twice the execution rate. So, yeah, okay. So that's how the two-stage works. The three-stage, we basically can even take more advantage because now you can be working at these all at the same time. But you can see here the no-op because it's waiting for the D to finish. And so it's idle. And so because of that, you got to throw in the no-op as well. And then you got a four-stage, which is a little bit beyond the scope. But just thought I would show that, just to show an example of pipelining with risk. Definitely read that section because they do talk about delayed branch, which is a very interesting topic. And also loop unrolling. It's a nice little idea that is worth exploring very quickly here. So one of the ways to improve code at compile time even is if you have code which has a loop, sometimes compilers, if your loop is only running like 3 or 4 times, what they will do is they will unroll the loop. What that means is that they will take the code and actually just expand it out as if you didn't have a loop. So basically just copy paste the code 3 times beneath it basically. Doing this removes any sort of issue with branching that you would have with the loop at the cost of making the actual code of the program longer, because now you have extra lines of code essentially. So you lose space at the gain of speed, because now you can you don't have to worry about this branching situation, and you can even run things potentially in parallel depending on what the code is and so on. So there's less jumping involved. So that's one very cool optimization of pipelining that you can do. Okay, and then delay branching and delay load are the ones that you should probably check out on your own time as well. Okay, but yeah, that's pretty much it. I think that's all that I wanted to cover about it. Let me see. Yep, pipelining. So the remainder of the book that we don't cover here in summer is going to just kind of, I mean, you can, if you bought the book, it's definitely worth reading, especially if you're, because you're eventually taking 370. A lot of the stuff they will cover in 370, but the book kind of at this point goes into talking about parallel programming and, for example, scalar, and how you can improve pipelinings with multiple pipelines, parallelizing stuff, the dangers involved with that, which again kind of introduced a little bit here with the data hazards, and all the extra sort of complexity involved when you have superscalar processors. And so that's basically like chapters 18. 19 is it's just basically talking about micro operations and understand the difference between like a hardwire control and microprogram control. So it's kind of specialized. But then chapter 20 is the one that maybe if you have time, it would be also worth reading, which is called parallel processing, which is something that they will, again, that's heavily focused on in 370. So it would be nice to read it as well. Especially 20.5, where I'm looking now, they talk about clusters. It's actually very, very good information to read. So I highly encourage you to take the time to check it out. And then they revisit, for example, like multi-threading and how pipelines get involved with that, which gets pretty cool. And so 21 also has more of an overview of multi-core computers. And they gave an examples of like an i7 59 or whatever. And then I think that's pretty much where the book ends with chapter. Is there chapter 20? Is there chapter 22? I don't think there is. There's an appendix, which, yeah, that was just whatever. So, yep, that's pretty much there. Oh, well, check the appendix G for additional pipeline topics. Actually, that has some really cool things about the pipeline reservation table, which is something that we didn't talk about, but it's all in the idea to improve pipelining. So you can check out that. Tomasulo's algorithm, that's actually kind of cool too, and so on. But yeah, that's pretty much the book. That's the whole book. If we had time, we would cover this probably in the regular semester. But again, they will be covering this in 370, so I don't feel bad about that. Otherwise, I'd probably make an extra video. So again, for tomorrow's class, there you are going to be watching the quantum computing, which I promised to have something on that. So I found that video, watch it. It's pretty good. If you have questions about it, you can go on. You can post on Discord, and then on Thursday you have basically the discussion session with the TA, which you can review the exam and things like that, and go over this stuff. Maybe do some examples of pipelining and things like that, and so on. So with that, we are to the end of the class. I'll try and stop by the discussion session on Thursday, say bye. But if not, then good luck in your test. I will be on Discord. Thanks for watching. Hopefully we got through together. This is indeed the first time that I teach this class. It was quite an interesting experience. Definitely the hardest class to teach of the classes that I've taught, because teaching programming is super easy and teaching data structures is even easier. But this class was quite something. So I definitely tried my best to try and cover at least a little bit of the broad world of computer organization, and hopefully I prepared you for future classes. But if not, then let me know. I guess. But I hope that you guys got some good knowledge out of this and that you enjoyed the class. And I hope that the project that we did, the IIS computer, is meaningful, because this is a class where you're not just grinding code. You get one program for the full class, multi-phase, sure, but I think it really does help to reinforce the contents and to respect how much complications are inside of a computer to be able to go and watch Facebook, whatever. So, yeah. So with that, I hope you guys have a good and safe summer, and good luck in your test. Be in touch on Discord. Thanks for watching. Don't forget to like, comment, and subscribe, I guess. And with that, I bid you farewell until next time. Stay safe and have a wonderful day. Good luck out there, guys.